find all values of d so that the average value of the function 3x squared minus 6x plus 7 for x between d over 2 and d is 5. All right, good. Now let's start with making sure we understand what is the average value. Okay, so the average value has a very particular meaning. So just as a reminder, what's going on, it says, suppose you have some function, you're going from a up to b. What you're trying to do is you're trying to find essentially a rectangle. We brought this high here so that the area of the rectangle would be the same area as the area under the curve. So that's the idea. Now, how do you find it? Well, you say, I know the area under the curve. That's what integrals do. So a to b f of x dx. And then I say, well, that's the area divided by that dimension, 1 over b minus a. That gives me my height. And so this is our average value. All right, so in other words, we're going to plug in d over 2 for a, d in for b, and this function for the function. And we have the is 5 equals 5. And that's great. That's going to give us exactly what we need. It'll give us an equation in terms of d, and then we'll solve it. All right, so let's begin. So we have, I'll start with the 5 is 5. So 5 equals 1 over d minus d over 2, and then the integral d over 2 to d of the function 3x squared minus 6x plus 7 dx. All right, well, let's work on simplifying. Now in the front, d minus d over 2 is d over 2. But that's downstairs, right? So we're going to bring it upstairs, and we do it by turning it over. So that becomes a 2 over d. And now we integrate. Integral of 3x squared, x cubed. Integral of minus 6x. Well, that's going to be minus 3x squared, right? Our rules, add 1, divide by the power. Add 1 to 2, divide by 3. Add 1 to 1, divide by 2. Here, it's like x to the 0. Add 1, 7x, and then divide by 1. Evaluate d over 2 to d. All right, well, this becomes 2 over d times d cubed minus 3d squared plus 7d. Subtract d over 2 cubed will become d cubed over 8. So we got to cube the 2. D over 2 squared will become d squared over 4. And d over 2 will be d over 2. Okay, that's not so bad. All right, well, let's work on combining. And okay, so this is equal to, we'll come back up here. We have our 2 over d in front, and we'll clean that up in a second. Our d cubes. Now, what do we have? We have 1 here minus 1/8. All right, let's do a little bit of work here. So 1 minus 1/8, that's 8 over 8, minus 1 over 8, 7/8. So we have 7/8 d cubed. Now, the squared terms. We have a minus 3 plus 3/4. So minus 3 plus 3/4. Now, minus 3, that's minus 12 over 4, plus 3 over 4, and minus 12 plus 3 would get us to minus 9. Okay, so minus 9/4 d squared. All right, good. And I'm always a little bit hesitant, so just going to quickly double check. Minus 3 is minus 12/4 plus 3/4. Yeah, that looks good. All right, then we have 7 and then minus 7 halves. Well, that one I could do. 7 minus 7 halves is 7 halves. Okay, good. So there we've grouped, and we can distribute the 2 over d through. And when we do so, what do we have? Well, the 2 goes in 8. That leaves us with the 4. So we get 7/4 d squared. And then here we get minus 9 halves d. And then at the end, we'll get 7d. All right, so that was just a distribution. Now remember, all of this, if you work your way back, equals 5. And when I said 7d, I was wrong. I shouldn't have said that because the d's canceled. Check your work. Check your work. So this equals 5. And so if we move the 5 across, that says we get the following equation. We have 7/4 d squared minus 9 halves d plus 2 equals 0. And now the end is in sight. What do we have? Quadratic. And if there's one thing we know, or at least hopefully we remember, is how to solve quadratics. All right, well, maybe we'll get lucky and it factors nicely. So let's clear out and let's get rid of fractions. So I'm going to multiply everything by 4. So doing that, we get 7d squared minus 18d plus 8 equals 0. All right, so we multiplied everything by 4, so we don't have any fractions. And we look at that and say, aha, I don't know how that factors. That happens. That happens. Well, we don't know how something factors, then what? Well, we always have the quadratic formula, right? Right. Okay, so let's do the quadratic formula. So d is equal to negative b. So here, negative 18 makes a positive 18, plus or minus the square root of negative, well, I shouldn't say negative b squared, just b squared. Now 18 squared, that's a big number. So I'm going to write that as, I'm going to write it as 2 squared times 9 squared. I'm going to cross my fingers and hope that something pulls out. And then we have minus 4, and then a, which is 7, c, which is 8. All that over 2a, 14. Now, look, there's a factor of 4 there. There's a 4 there. So, with that, I say, oh, I could pull the 4's out, and the square root of 4 is 2. So this becomes 18 plus or minus 2. And now I feel better. I have 81 subtract 7 times 8 is 56, all over 14. Now, 81 subtract 56, if we've lived a good, clean algebra life, will be a nice number. Or maybe if we assume that our instructors love us, but of course they do. They're the coolest people, those math instructors. Can you see what 81 minus 56 is? 25. And square root of 25 is nice. All right, so we'll make some notes here. This is square root of 25 equals 5. So what we really have here is we have 18 plus or minus 2 times 5, which is 10, all over 14, which leads to two possibilities, 18 plus 10 over 14, and 18 minus 10 over 14. Now, 18 plus 10 is 28. 28 divided by 14, also known as 2. 18 minus 10 is 8. So that's 8 over 14. Or divided by 2, that's going to be 4 over 7. And so it turns out that there are two possible values for d, and our answers are 4 7s and 2. And there we go. Whew. Okay, so it got a little messy towards the middle part, if we count the middle part as being, this. But the setup we understand. it's saying compute the average value and set it equal to a number. And then it's just a matter of patiently plugging in, checking your work, making sure you don't do any silly mistakes, and then working through the quadratic formula if you don't see how to factor. And it's perfectly fine to use the quadratic formula. And then we get it. Life is good. We survived this problem. No, let's not say we survived. We thrived. We thrived this problem, right? We got this. We can do these things. We're pretty awesome, right? Oh yeah. Find the integral, and we have bounds, square root of a third to 1 of 3x squared plus 15 over x squared plus 1. All right, good. So this is a definite integral. And this is one that we're not going to try to use any geometry on. We're going to use our big tool. What's our big tool? The fundamental theorem. Because that seems like it's going to be very fundamental for us to solve these types of problems. Now this might feel familiar, kind of like we saw something like this last week in the previous quiz. And that's because we kind of did. And so we're going to say, hey, those ideas worked pretty well. And generically speaking, what's our goal? We say there's only a handful of things we actually know how to integrate. So what we're going to do is work our way until we get to one of those things, or maybe a collection of those things. Now here, what can we do to help us on our journey? We can do some long division. You can also do a little bit of like add and subtract, but more or less it's really the same thing. So let's go ahead and just call it long division. Call a long division problem a long division problem. All right, I'm going to write this as 3x squared. I'll put a placeholder since there's no x in case we need it, plus 15. Work with your leading terms. I have x squared. What do you multiply x squared by to get 3x squared? 3. All right, so we put a 3 there. Multiply 3 by x squared plus 1. And say, okay, what's left for me to account for? Well, when you subtract out what this would account for, you say, all right, I don't have anything with x, and so what's left is 12. And then we say, wait, stop, because 12 has less power than x squared. So our division is done. Now, how do we read this? We say this means this is equal to the integral of the square root of 1/3 up to 1 of, and then we have 3 from this part right here, then plus our remainder, 12, over x squared plus 1. All right, so there we go. Now, let's integrate. Okay, so each one of these pieces is something that we can integrate. The integral of 3 is 3x. All right, well, that's good. What about the 12 over x squared plus 1? Well, the 12 comes out, and the integral, now here when I'm using the word integral, I really mean antiderivative. They're interchangeable in many cases. It's arctangent. Oh man, this feels like a problem I would have written. It wasn't, but it feels like it. All right, and then we evaluate. Because remember, what does the fundamental theorem of calculus say? It says that if you want to do a definite integral, find an antiderivative and plug in. So we're like, hey, we want to do a definite integral. So we've been working to find an antiderivative. We succeeded, yay us, and now it's a matter of plugging in. All right, so what do we now have? We plug in 1. 3 times 1, 3 plus 12, arctangent of 1. We'll come back to that. Subtract 3 times square root of 1/3. We'll come back to that. And 12 arctangent of square root of 1/3. All right, now I want to make a note here of something that I have found incredibly useful. And it's something that if you just get into the habit of soon and just keep it, you're going to save yourself a lot of points. And we love our points, right? See, there's this special technique, and it's called use parentheses, right? So how do parentheses work? You put parentheses around things. Why do we put parentheses around things? Well, because we want to make sure we don't lose information. So in this case, there's a minus here. We want to make sure it's not just the first term, it's also the second term that gets the minus. Use your parentheses, get your points. All right. Now, how do we find these numbers? Well, for that, you kind of need to know a little bit about tangent. Not a lot, but a little bit. And so let's talk about some tangents of common angles. So we'll make a little chart here. So we'll have theta, and then we'll put tangent of theta. And so we'll do 0, pi over 6, pi over 4, pi over 3. We'll even throw in pi over 2. Now pi over 2 is, technically it's undefined. Oftentimes we think of it like infinity, but undefined. Tangent of 0 is 0. Tangent of pi over 4, that's a classic angle, that's 1. Now what about pi over 3? Well, you can think of sine of pi over 3 divided by cosine pi over 3. Now that might help a little bit. Sine of pi over 3 is root 3 over 2. Cosine of pi over 3 is 1 over 2. When you divide, the over 2's cancel, so you get a root 3. What about pi over 6? Well, sine of pi over 6 is 1/2, and cosine of pi over 6 is root 3 over 2. Kind of like the opposite. These angles are complementary, so that's not too surprising. So when you divide, you get 1 over root 3, which, by the way, is the same as root 1/3. So when we say arctangent of 1, it's like scanning, where do you see 1 as an output? Like, hey, there it is. What's the angle? Pi fourths. So this is pi fourths. Then what about this root 1/3? Okay, scan, 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 scan. Ah! Okay, and what's the angle? Pi 6. So this is a pi 6. Now here, 3 times 1 over root 3, you can really think of this as 3 to the 1 times 3 to the minus 1/2. So when you put these together, you add and you end up with 3 to the 1/2. So what do we have? We have 3. 12 times pi over 4 would be 3 pi. Subtract root 3, 3 to the 1/2. Now 12 times pi over 6, that would be 2 pi. So plus 2 pi. And now, well, let's clean up just a little bit more. We have 3 pi subtract 2 pi is pi, and then minus square root of 3, and there we go. That's our answer. 3 plus pi minus square root of 3. Woohoo! Nice! It's almost as easy as pi. All right. Well, I guess the good news, of course, is now that we have this fundamental theorem of calculus, it makes doing integrals quite a bit easier in cases when we can find antiderivatives. It's definitely a lot easier than Riemann sums. And so this is going to open up a whole new world for us. It's going to be a lot of fun. Let's enjoy the ride together. Oh yeah. Evaluate the finite sum where n is a positive integer constant. Give your answer as a single fully reduced fraction. So it's like we have a sum and we say, look, I don't want to have a sum, I want to collapse it. I want to get it down to a single expression. And this is something that commonly happens, especially when you're doing Riemann sums. It's like, well, I have lots of terms. I don't want to look at lots of terms. I want to say, what's it equivalent to as one term? And then we can figure out what's going on. All right, well, so for us, let's think about what we can do. Now, we have a couple of things. We can say sums behave like addition, because that's what they are. And so one of the things we can think about are, 1, can we pull out anything? 2, can we break it apart? Now, what are we allowed to pull out? What aren't we allowed to pull out? Well, what we're not allowed to pull out is anything with a k, because k is not a fixed quantity, it's a changing quantity. And so since every term, the k will be different, I can't pull it out of the sum because it's representing a lot of different things. Sometimes it might be a 3, sometimes it might be a 24, sometimes it might be 109. I don't know what it is. So it can't pull out to the front. So I can't pull out k, but if it's not a k, it's a constant with respect to k, so I can pull that out. So in particular, notice the denominator, you have this n cubed, doesn't depend on k, that can pull out of the sum. Now the other thing is that we can break our sum up. In other words, sums are linear, and linear things work great when we talk about with respect to addition and scalar constants. We have that plus sign there. So what we're going to do is we're going to break it into pieces. All right, good. So let's say, what is this sum? Let's clean it up. Well, this is the same as the sum of k equals 1 to n of k, and pull out 6 over n cubed. So that's the first piece here, plus 2 over n cubed, the sum k equals 1 to n of 1. So that's the second part. All right, so we've pulled it apart, and we've pulled out the things that we don't need. Now we have two simpler sums to deal with. One of them is really simple, which says, this sum says what? We're going to add 1 plus 1 plus 1 plus 1. And what's next? Plus 1 again. Like, wait, is it always going to be plus 1? Yes, you've mastered the secret. We're always adding 1. Like, whoa, okay, cool. So if you add 1 n times, because we start at 1, go to n, how much do you have? You have n. Whew. Okay, now this sum is a little bit more interesting. It says start with 1, then add 2, then add 3, then add 4, and you keep going, and eventually you stop. All right, how much do you have? Well, what you can do, it's a beautiful argument, and there's lots of ways to prove this, by the way, but let's suppose you say, look, let's add 1 to the end of the first bottom row. Then let's add 2 to the next row. Then we'll add 3, and we'll just go back up. And what will happen is that we will have written down the same number of dots twice. But how many dots do we have in total? Well, in one direction, we're going to have n dots. And then in the other direction, we'll have n plus 1 dots. So the number of dots in total is n times n plus 1. Half of them is what we want. So n times n plus 1 over 2. Now that's what we're after. And, I have a small typo here. Let me fix my small typo. It's supposed to be n, like that. Haha. Check your work. Make sure you copy. Sorry about that. All right, now, what do we do? Well, let's update what we have. So this is 6 over n cubed times, here, it'll be capital N times n plus 1 over 2, plus 2 over n cubed times capital N. Well, 2 goes into 6, and we can knock out an n there. And here, we can knock out an n there. So we have 3 times n plus 1 over n squared, that's from the first term, plus 2 over n squared. All right, and now, see how we use that plus to break things apart? We can do it to put things back together. They already have the same denominator, so it's going to be pretty straightforward. We'll have 3n plus 3 plus 2. So that makes 3n plus 5 divided by n squared. And we're done. It's a single fully reduced fraction, there's no sum, right? There's no sigma. We've gotten it. Exactly what they asked us to find. Woohoo! Nice! So, by the way, the fact that this sum looks like n times n plus 1 over 2, classic. You can always rederive it, but it's one of those ones that maybe you might want to remember. I wouldn't be surprised if it shows up. Write the following sum using sigma notation and use that to calculate the sum. So here we have 3 plus 12 plus 21 plus 30 plus ... plus 84. And we want to say what's going on. Now, by the way, ... what is this stand for? It's shorthand notation for, and the pattern continues. So it's not to say, oh, it's 3 plus 12 plus 21 plus 30 plus 84. There's a bunch of other numbers that we didn't write down. And so we have to say, okay, so what is the pattern? So this is a fun game of like, can you spot the pattern? We have a bunch of numbers here. What can we say? And in particular, a common pattern to look for is to say, look at the differences. How far apart are these numbers? 3 to 12, what happened? Well, we went up by 9. 12 to 21, we went up by 9. 21 to 30, we went up by 9. So it's like, oh, what's happening is we're starting at 3, and then we're taking steps of size 9 until we get to 84. All right, so that's good. That makes some sense. And so how do we take steps of size 9? Well, it says we take 9 times whatever our current number is. Okay, so there's sort of a clue. 9 times something. Now, we aren't just factors of 9. We have some other terms as well. So we have to account for that. So we say, okay, let's suppose we say we want to start at 1, just because we're so used to starting at 1. What do I have here? Well, 9 times 1 is 9, but I don't want 9. I want 3. What should we do to it? Well, to get from 9 to 3, I subtract 6. Now you might say, wait, what? How do you say 9? That's 9k. So right now I'm thinking, and I'm like, okay, so there's like, it's 9k plus something, right? So I'm trying to think, what's that something? And so consider the first case. So here, when we put in k equals 1, we would say, aha, when k equals 1, this is 3. When k equals 2, 9 times 2, 18 minus 6 is 12. When k equals 3, 9 times 3 is 27, minus 6, 21. When k equals 4, 9 times 4 is 36, minus 6 is 30. So this is good. Now, where do we stop? Well, that's actually kind of a useful question to know. So what's going on? Well, we have 9 times k minus 6, and we want it to be 84. So we can add the 6. It says 9 times k equals 90, or k equals 10. So we're going to go up to k equals 10, and then at that point, that's when we stop. So now it's like, oh, okay, so using our sigma notation, this would be the sum where we start at 1, we go to 10. 1 to 10 of 9k minus 6. All right, now that's part of our answer. So before we go on, let's do some recap. Like, where did these terms come from? So this 9 here, we identified by looking for what are the gaps. We were expecting consistent gaps, and we got consistent gaps. So that's the gap. Now we're going to start our sum at 1. We say, okay, given that we look like 9 times k, and what do we need to add or subtract so that the first term is right? So we said, okay, when k equals 1, we have 9 times 1 is 1. I want to get to 3, so I need to subtract 6. So that fixes the first term, but it will also fix all the rest of them as well. So that's where the minus 6 came from, so that we made sure the first term was right. We also said, how do you figure out the last term? Like, where do you know where to stop? So set the 9k minus 6 to the last number. Solve for k. All right, so that's how we found our stop. Now, we have to evaluate this sum. That's okay. We can do that. So, since we're doing a different idea here, let me switch colors. All right, I have a different color here. So here's the idea. What we're going to do is we're going to take advantage of linearity. All right, so we say, hey, we've got a nice subtraction here. Let's go ahead and use that to break it up into two easier to digest sums. So this is the sum, k equals 1 to 10 of k, but pull out the 9, minus 6, sum k equals 1 to 10 of 1. Now, both sums are pleasing. In other words, sums that we're familiar with. So if you have sum k equals 1 to 10 of k, well, it really says the way you find it is, let's assume you start at 1, and it looks like k, then the answer says you do the number you stop at times that number plus 1, all divided by 2. And so we'll write that down here in the corner. The sum k equals 1 to n of k is n times n plus 1 over 2. All right. Minus 6, and then this sum is 1 plus 1 plus 1 plus 10 times, so times 10. All right, well, 2 goes into 10, that's 5. So we have 45, which is this number, times 11, and then minus 6 times 10 is 60, and 45 times 11 is 495. Now, if you're like, how did you get that so quickly? It's 450 plus 45. And so you add, and you get 495. So it's not too bad. And now subtract 495, subtract 60 is 435. And there we go. That's our answer. Nice! Cool. And, all right. Well, pretty good. Pretty good, right? Yeah, it's wonderful. It's wonderful. Now, you might notice something, and I don't know if perhaps this is the most helpful thing to point out, but let's go ahead and point it out anyways. Suppose you do have these things which are equally spaced, so this is just a check. Add the first and the last. What do you have? 87. Okay. Times that by how many terms you have? Well, how many terms do we have? We have 10. That's 870. Okay? Now, divide by 2. 435. That will always work in the case when things are equally spaced. Add the first and the last, times by the number of terms, and divide by 2. And that'll give you the same sum. That's a check, but keep in mind, they want you to go through this process. So, all right. Well, another problem down. Nice. Use the fundamental theorem of calculus to compute f of 4, where we're told that the integral from 0 to x of f of t dt is x squared e to the 3x. Now there's two flavors to fundamental theorem of calculus. One flavor is if I want to do definite integrals, find an antiderivative and evaluate. But another flavor says, hey, you know, if you're finding a cumulative total, in other words, something that looks like this, then that's an antiderivative. So if you take the derivative of that, you get back to where you started. So put another way, the derivative of the integral from a to x of f of t dt is f of x. So this is the fundamental theorem of calculus. So, idea, we pretty much have that right there. A is any number. Turns out 0, true story, is a number. So, let's take our equation that we were given, 0 to x f of t dt, okay, that's equal to x squared e to the 3x. And now we're going to take the derivative of both sides. All right, so we have that the derivative of the integral is equal to the derivative of this function. All right, the derivative of integral of 0 to x f dt is f of x. Well, on this side, use your rules. So we have the derivative of the first, 2x, times the second, plus the first, x squared, times the derivative of the second, 3e to the 3x. Now this gives f for any value of x. What do we need? F of 4. So we plug in f of 4 equals 2 times 4, 8. And we have e to the 3 times 4, 12, plus 4 times 4, 16, times 3, 48. E to the 3 times 4, 12. All right, well now, 8 plus 48 makes 56. E to the 12th, e to the 12th. And we're done. That's it. That's all we need, right? Because we just said find f of 4, and we found it using the fundamental theorem. So, woohoo! Nice! We should have more problems like this, right? We can always hope. Expand and simplify the sum from k equals 0 to 4 minus 2x to the power k plus k squared minus 5k plus 4. All right. Now, for things like k squared and k, we have equations for. The k squared, we may or may not have it stored in memory. But what do we have? We also have this minus 2x to the k. Well, there's ways to do that, but not really cleanly. So here we're not going to try to come up with formulas. We're just going to brute force it. And the sign that brute force is actually probably what they want us to do, the strategy, is notice that these are small numbers here. We're starting at 0 and going to 4. Be careful where you start. Sometimes you start at 1, sometimes you start at 0. Maybe someday you'll start at 2. Who knows? So pay attention. Pay attention. Do what the problem states. And so sometimes they do something a little different. So let's just work this out. So we're going to go ahead and just plug in k equals 0. And what do we have? Minus 2x to the 0 power. And by convention, something to the 0 power, except for 0, is 1. You might say, wait, what's 0 to 0? More work. Okay, but all right, generically it's 1. 0, 0, 4. So for k equals 0, we get out 5. For k equals 1, well, we have minus 2x to the 1 plus 1 minus 5 plus 4. Well, hey, well, that's very convenient. 1 plus 4 is 5, minus 5 is 0, so we get out negative 2x. All right, now let's plug in 2. Minus 2x quantity squared, well, that would be minus 2 squared is a 4, so it's positive 4x squared. K squared would be 2 squared, that's 4, minus 5 times 2 minus 10, and plus 4. So we get 4x squared, and here it's minus 2. All right, for k equals 3, minus 2 times x quantity cubed, but minus 2 cubed is minus 8. And then we have x cubed. 3 squared is 9. 5 times 3, minus 15, and plus 4. Now, 9 plus 4 is 13, minus 15 is a minus 2. So we have minus 8x cubed minus 2. And our last one, k equals 4, right? Because we need to start at 0, end at 4. 0, 1, 2, 3, 4. Minus 2 to the 4th is 16. X to the 4th, And then we have k equals 4 squared and 7 years ago. No, wait, no, that's something else. Okay, so k squared, 16. 5 times 4, 20. And then plus 4 is plus 4. 16 plus 4 is 20. Subtract 20 is 0. So we get 16x to the 4th. Now I'm going to just put this over here. And now what's the punchline? Well, the punchline here is we want to add these all up. So, right, because we're going to add up what happens at time 0, at time 1, time 2, time 3, times 4. So we're going to get a polynomial. Let's deal with our powers of x. We have 16x to the 4th minus 8x cubed plus 4x squared minus 2x. Now for our constants, we have a 5, a minus 2, and a minus 2, and everything else is 0. 5 minus 2 leaves us with 1. So 16x to the 4th minus 8x cubed plus 4x squared minus 2x plus 1. And there we go. That's our polynomial. Nice! That's actually kind of a very pretty expression. And but the moral is, that's what we're going to end up with. So, woohoo! Find the equation of the line tangent to g of x, which can be written as the integral from 3 to x of 4t squared minus 12t over t cubed minus 12 dt at x equals 3. Cool. Now, looking at this, it feels like, so does that mean we've got to integrate this? Because looking at this particular expression, 4t squared minus 2t divided by t cubed minus 12, there's a term that we give to this kind of integral, which is not nice. This is an integral we would not want to do. It is unpleasant. Okay. And so I was like, well, wait, if we can't find g, how can we find the tangent line? Well, what do you need for a tangent line? You don't need the whole function. You need just a little bit of information. In fact, we need to know 2 things. So if we're after a tangent line at x equals 3, well, we really need to know, what does g of 3 equal, and what does g prime of 3 equal? Everything else, we don't really care what g does. We just say what happens at 3. So let's start with g of 3. So when you want to find g of 3, what do? You plug it in. So, all right, g of 3, what happens when we plug in 3? We have the integral from 3, and everywhere we see an x, we're putting in a 3, so the 3 of 4t squared minus 2t over t cubed minus 12 dt. Now, in general, hard integral, but this is a definite integral, and we can take a look at it and say, something very suspicious seems to be happening. What do you notice? The bounds match. If the bounds match, what's true? 0. There's no area here. There's no total. Because it says, okay, I'm going to start. Stop. Wait, what? I just barely started. Yes, stop right away. I haven't done anything. Exactly. 0. So when the bounds match, we get 0. So it's like, we're halfway. Woohoo! All right. Well, what about g prime? So now that says, well, I want to know something about the derivative. And it's like a derivative of an integral? That sounds like it would be very mental. No. It's very fundamental. Okay, so let's look at g prime. So g prime of x, that's the derivative of x of integral 3 to x of 4t squared minus 2t over t cubed minus 12 dt. Okay, well, when you take the derivative of the cumulative total, that's what this is, what do you get? Well, the answer will probably not surprise you. You're going to get the function on the inside. So, fundamental theorem of calculus, that's what we're using here. FTC, fundamental theorem of calculus. this is equal to 4x squared minus 2x divided by x cubed minus 12. So literally everywhere we see a t, we're putting in an x. Isn't that nice? It makes things pretty easy. Now, what do we need to do? We need to plug in 3. So we say, okay, what is g prime of 3? Well, it's 4 times 9 minus 2 times 3 divided by 3 cubed minus 12. That's 36 minus 6 over 27 minus 12, or 30 over 15, or 2. So g prime of 3 is 2. All right, so we have found all of the information that we need to find this derivative. We know what the value of the function is, and we know what the value of the derivative is at the point where we're interested in. So we're going to put all of this together and say, well, what's our tangent line? And it is y is equal to g of 3 plus g prime of 3 times x minus 3. That's just the generic formula for it. So in our case, g of 3 is 0, so you get y is equal to g prime of 3, which is 2, times x minus 3, which we can also write this as y equals 2x minus 6. And we're done. All right, good times, good times. Yeah, woo! That wasn't so bad. It looked intimidating, but we were not intimidated. We persevered. We did great. Find the integral from 0 to 2 of 3 square root 4 minus x squared minus 2 quantity squared. Whew, okay. Well, yeah, let's figure this out. Okay, now, not recognizing this function right away, we say, is there anything we can do to rewrite it? And we can't help but notice we see a square here, so probably we should square it. That's right, we're going to do some algebra. We're going to have some fun with algebra. All right, now, notice, think of this as your a minus b. So we're going to have 9 times 4 minus x squared. This is your a squared minus 2ab. So 2ab. So we're going to take 2 times a times b. So that's 2 times 3 times 2. That's 12. Square root 4 minus x squared. And then plus 4, and that's your b squared. So a minus b squared, a squared minus 2ab plus b squared. All right, dx. And now, let's see, can we do anything to make this look maybe a little bit nicer? Well, we can distribute here, then combine. So this is the same as the integral 0 to 2. 9 times 4 is 36, plus 4 makes 40, minus 9x squared, minus 12 square root 4 minus x squared dx. Okay. Now, the good news is, whereas this originally looked kind of like intimidating and not so clear that we can make any progress, we now look at this and say, hey, this first term looks great. This second term, we can recognize that. This third term, we'll think about that. So let's break this into 3 pieces. So we're going to use linearity of integration. So this is the same as the 40 integral 0 to 2 of 1 dx minus 9 integral 0 to 2 of x squared dx and minus 12 integral 0 to 2 of square root 4 minus x squared dx. All right, let's talk about these one at a time. So for the first one, integral from 0 to 2 of 1, well, integral of 1 is pretty straightforward. It's x, and then evaluate 0 to 2. Well, plug in 2, you get 2. Plug in 0, you get 0. And so this comes out to 2. How about this part, x squared? Well, integral of x squared, add 1. When I say integrals, it means antiderivative. and divide by the new power. So it'd be x to the third power divided by 3. And then we're going to evaluate from 0 to 2. When we plug in 2, 1/3 times 2 cubed, that's 8/3. Plug in 0, you get 0, so we're left with 8/3. Now this last integral, it's not looking promising. It's not on our list. There's not some kind of fun algebra you can do. And I know you're thinking like, oh man, you know what you could do, Steve? I've seen this before. It's been cool, right? The square root of 4 minus x squared is like 2 minus x, right? No, 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 it is not. And I know it's tempting, but it is definitely not the case that the square root of 4 minus x squared does not equal 2 minus x. Okay, square roots don't mix well with addition and subtraction. Essentially, you can think of it as multiplication and addition don't always mix well together. That's what it boils down to. So you guys say, well, okay, well, what can you do? Well, let's try to understand this for a second. Suppose we think about the function y equals square root of 4 minus x squared. Say, well, I don't like the square root. Great, I'm not a big fan either. Let's get rid of it. Y squared equals 4 minus x squared, or x squared plus y squared equals 4. Ooh, that seems very circulaceous, which is to say, like a circle. Like a circle, seeing it for the very first time. Yeah. All right. No. All right. So what is this a circle of? Well, it's a circle of radius 2 centered at the origin. Now, running backwards, see how it's the plus part? That just means we only look at the top half. All right. And then we say, so it's the top half of a circle. Now notice our bounds are going from 0 to 2. So it's like, so it's like we're trying to find this area. Oh, so this is 1/4 of a circle. Now the area of a circle is pi r squared. So we can find that area. In particular, 2 squared is 4, divided by 4, this is pi. So let's see what we have. We have 40 times 2, 80. Subtract 9 times 8/3. Well, notice that 3 goes into 9. So this is really going to be the same as 3 times 8. So 3 times 8, 24. Minus 12 pi. All right, now 80 subtract 24 is a number. It's 56. And so we end up with 56 minus 12 pi. And there we go. We found our answer, and it was not so bad, right? Broken into pieces where we could do it using the antiderivatives, and another piece where we could do it by saying, circle. It's a circle of the answer. So I will say at this point, pretty much the only two things we can do, which is not antiderivative, are circles or symmetry, in particular odd functions. And so as soon as you start seeing a square root, you're like, could that be a circle? Could it be a circle? You know, like that should be like a little tiny nagging voice from the back of your head. Maybe nagging isn't the right word. A loving, sweet, cooing voice. Oh, we love those circles. Maybe it's a circle. All right, well, another one down. Success. Or as Klingons say, kapla! The velocity of a particle is given in meters per second by this function. And it's an integral log of t to t squared cosine pi of x cubed dx. Find the acceleration of the particle at time t equals 1. All right. Well, how do velocity and acceleration relate? If we have velocity, to get to acceleration, take a derivative. So it's like, oh, okay, so let's take ourselves a derivative. So acceleration of t is the derivative of velocity of t, which is the derivative of the integral log of t up to t squared cosine pi x cubed dx. Now, we're going to take this derivative. I want to point a couple things out. There's a couple things that might make people uncomfortable. I just want to point it out loud, because the sooner we recognize it, the quicker we can say, that's okay, we can deal with it. Normally when we deal with this kind of expression, we're taking the derivative with respect to x. We have functions of x here, and there's t's inside of here. We are now switching the roles of t and x. Is that okay? Yes! They're symbols. They can be switched, and they can change roles. That's perfectly allowed. No problems. No problems at all. We're cool with that. All right? Okay, so we wanted to say that out loud. Now, there's another thing that's going on that's a little interesting here that I want to make sure we remember, which is to say we have functions both in the upstairs and downstairs part of the integral. So it might behoove us to remember that formula. So I'm going to write that down. So here we go. If we have the derivative, and I'll use it using this notation, derivative with respect to t of the integral from h of x to g of x, h of t to g of t, even me, see, I got thrown off. All right, let me start that over. So if we're taking the derivative with respect to t of the integral from h of t to g of t of some function f of x dx, then fundamental theorem of calculus mixed together with chain rule, mixed together with properties of definite integrals, says you do the following. You say, all right, start with the top, and what you're going to do is everywhere where you currently see an x, put in the top. So that's f of g of t. And then chain rule kicks in times the derivative of what you put in. So it's the derivative of the outside, it's the f, g of t is on the inside, times the derivative of the inside. Subtract, now you do the bottom. So again, everywhere you see x, you put in h of t. F of h of t times the derivative h prime of t. And there you go. So that's the generic formula. All right, so we're going to do the same thing up here. So here we go. So we don't have to think too hard. We just follow the formula. So we're going to plug in. Actually, let me change colors here so you can separate what happens with the two parts. So we'll do the upstairs part first. So we'll plug in everywhere we see an x, only one place, put in t squared. So this is cosine pi t squared cubed. All right, now times by the derivative of what you plugged in, 2t. Subtract, okay, and we're ready for the next leg. And for the next leg, let's see, I have another pen here, by great coincidence. All right, so now we're plugging in log t. So this is cosine of pi log t cubed times the derivative of log t, 1 over t. Now, this is not the answer. What this is the acceleration function at any time t. So, how do we get our particular acceleration? We plug in. So we're like, oh, all right, now let's just plug in 1. So, a of 1, according to this, we'll take cosine 1 squared cubed. Well, it's 1 times 1 to 1, it's 1 to the 6, right? So this is cosine of pi, and times 2 times 1. So cosine pi times 2. We'll clean that up in a second. And here, log of 1. Log of 1 is 0. 0 cubed is 0. So subtract cosine of 0 and times it by 1 over 1. So times that by 1. Okay, good. So we plugged in t equals 1. Now cosine of pi also goes by negative 1. So this is really minus 2. Cosine of 0 is positive 1. So minus 1, which gives us minus 3. That's our answer. So great. We'll box it. Now, I left some suspicious space here because they didn't ask us for units in the answer, but they kind of gave us units in the problem, which is kind of weird. And so we're not required to put them because the problem didn't ask for it. But as a sign of good faith, let's go ahead and figure it out. If our velocity is meters per second, what is our acceleration? It is meters per second squared. All right, so we're ready. If they ask us for units, we will give them units, but otherwise, negative 3, life is good. And we really are doing sort of testing our fundamental theorem of calculus with chain rule. And it's good to know, once you have this formula, like you'll just be taking derivatives of integrals left and right, and you'll be getting the right answers. And we love right answers, because that's where we get the points from. Got to get those points right. Got to get them all. Let f of t be shown in the graph. Okay, so here's f of t, and a portion of which is a half circle radius 2 centered at 1, 1. See this? Here's 1, 1, and it's a half a circle. Yep, they didn't lie to us. That is a half a circle. Now, if the function capital F of x is the integral from negative 3 to x of f of t dt, determine the following. All right, so question 1, find f of 4. Now, let's think about this. All right, so if we think about this, I'm plugging in 4 in for x. So this is the integral from negative 3 to 4 of f of t dt. So we're going to go from negative 3 to positive 4. And we want this area. And we can say, well, let's think about it. We can split it up into 3 pieces. We have this triangle, this very long rectangle, and this half circle. And because when we think about definite integrals, there's an area interpretation. Now, if we go for the triangle, what would that be? Well, triangle, we have a base of 2, height of 2. 1/2 base height would be 2. For the rectangle, we have 1, 2, 3, 4, 5, 6, 7. Or if you like, that's 1 high, 7 wide. So that's 7. Now for this half circle, it's half of a circle of radius 2. So 1/2 pi 2 squared. So 2 plus 7, here you can cancel off a single 2, plus 2 pi. So we can put our notes up here. F of 4 is equal to 9 plus 2 pi. Okay, so there's the first piece. Nice. Now, f prime of negative 3. You're like, aha, plug in negative 3. Negative 3 to negative 3 is 0, right? Oh, be careful. Notice, what do you see here? You see a prime. So we need to take a derivative. And this is a case where you want to pay attention, because sometimes it's very simplistic, like what you see here. Sometimes they throw functions into the bounds. So for us, we say, well, if we want f prime of x, that's the derivative with respect to x of the function. So we put in negative 3 to x of f of t dt. And we say, okay, fundamental theorem of calculus. This is just very basic case. Constant up to x will be the function on the inside. It's f of x. We say, oh, okay, well, that's f of x. All right, so what are we looking for? Well, we want f prime of minus 3. So that says that f prime of minus 3 is f of minus 3. So we come over here and we say, what's this value? And we see it's 3. So f prime of negative 3 equals 3. All right. Whew. Okay, 2 down. One last one to go. So for x between -5 to 6, on which open intervals, and the reason they put the phrase open intervals is, of course, there's always controversy. Should it be open? Should it be closed? It's contentious, but that's okay. They said open, so we'll go with it. Is the function f of x concave down? All right. So we have to start thinking about this. Now be careful here. This is not capital F of x. This is little f of x. As a result, it's not as easy to say as, oh, what's concave down in this figure? So you have to say, okay, what's this figure? Well, we actually know what this figure is. This figure here is the derivative. So we could say, okay, so this is the graph. This is the graph of f prime of x. And at this point, you're like, okay, so how do we use that? Well, now we start thinking about what do we know about concavity? Well, we often think about concavity as, how does the curve bend? But we can translate that into saying, well, concave up, concave down is really about what's happening with the derivative. So concave up, derivative is increasing. Concave down is derivative is decreasing. So concave down, we say, well, that really corresponds with the derivative f prime of x decreasing. And so now let's look at the picture. And let's mark all the places where the derivative is going down, strictly downhill, not flat, down. We say, well, we're going down here. See, we're flat. That doesn't count. We're going up. At the top, we start going down. Okay, so that's going to count. Here we're flat, so we're not going to count that. Then here we're going down again. So we have 3 places where our derivative is decreasing. And so we say, okay, those translate to where we're concave down. So f of x concave down in the following places. So this interval from -3 less than x less than -1. This interval 1 less than x less than 3. And this interval 4 less than x less than 6. And we're done. Woohoo! Nice! We made it to the end. And I think this quiz, the first one was a little tricky algebraically, but not too bad. We're kind of having our fun. We're dipping our toes into the fun parts of integration, right? When we really get to play with the fundamental theorems of calculus. Thank you so much for joining me. I hope you're enjoying these. I hope you're learning. I know you're a great person and that you can master these skills. Keep at it. Keep practicing. You're going to do wonderful. I believe in you. And let's do this one more time. We have one more quiz before the end is done, right? All right. See you again. Bye.